Now we're going to take a look at origin symmetry. So what I've done here is I've drawn a graph of a function that has origin symmetry. And what you'll notice is it's a slightly different relationship, but kind of similar to what we did before. If a function has origin symmetry, we would actually say if xy is a point on the graph of the function with symmetry about the origin, then so is the point negative x, negative y. So in this particular case, we would have pairs of points, and those pairs of points would have to be so that we have xy on the graph, and we also have the negative of x, comma, the negative of y on the graph for every single point. So functions with symmetry about the origin are called odd. I always tell students, if you can remember that one is even and one is odd, the two O's go together, so origin goes with odd, so therefore y-axis has to go with even. So if we write kind of a similar function statement as we did with the previous example, we would say if f at x is a function, then f is called an odd function if for all x in the domain of f at x, f at negative x equals the negative of f at x. So the graph of an odd function is again called symmetric about the origin. So notice when this one, if I want to prove that I'm symmetric about the origin, I'm going to again compute f at negative x, but this time instead of getting back to the original, what I'm going to get back to is the negative of the original. So let's do an example where we use this concept to prove a function is odd. So we're going to show algebraically that f at x equals 6x cubed minus x is symmetric about the origin. So like we said, we're going to evaluate f at negative x, which again means I'm going to substitute in negative x every place I see an x. So if I do that, I'm going to have f at negative x is equal to 6 multiplied by negative x to the third, with a negative raised to the third, minus, instead of x, it's negative x. So remember, do it every place. You have to put that negative x in everywhere. When we simplify, we end up getting f at negative x is equal to the negative of 6x cubed plus x. Notice this is the negative of the function we started out with. In other words, when we did f at negative x and managed to get our negative 6x cubed plus x, if we brought out a negative, that would be the negative of 6x cubed minus x, and so we notice that is in fact the exact negative of the original function. So therefore we can say f at negative x equals the negative of f at x. And again, when this occurs, we say the function is odd. Now, just briefly, a couple of last comments here. A function can be neither even nor odd. Okay, so we might have a function. So not all functions are even or odd. They could be neither that. So it's not like numbers where you might think, oh, every number is even or it's odd. There are some functions that are not either of them. Can you think of a function that's both even and odd? We'll be talking about that in class a little bit, so do a little thinking about that. And then, once again, you may have noticed we didn't discuss symmetry about the x-axis. We're not going to do that when discussing functions, because a graph that has x-axis symmetry isn't going to be a function. Okay, well, now you can go out and take a look at the problems that I asked you to do in the section, and then we'll move forward and we'll discuss these at a later point in class.